Our next speaker is Michael Gonzalez. He is a security consultant at RSM Australia. He previously worked as a computer programmer for a decade before shifting his career to InfoSec. Presenting his talk titled Highway 64, please welcome Michael Gonzalez.
Thank you, everyone. Let me fix this. Check my notes. So, hi everyone. First, I want to thank everyone who are here for my talk, and I hope you'll be able to learn something from it. So, the reason for my talk that came about is I want to share some of my experiences when doing thick client application testing. And yeah, most of the testing that I did with my previous clients were like in graphical user interface form or in like desktop application form, and not in like a console application form that you can find mostly on CTFs. So the agenda for this talk is, yeah, who am I, and going to the introduction of what is binary exploitation, uh, address bus and data bus, how are the in-memory CPU registers being used, and the types of calling convention, and how memory address are loaded into the CPU before they are being called. Next one will be the shellcode. What are the types of shellcode, and how can we use them? And finally, the demo. So who am I? Yeah, just what she said. I'm Michael Gonzalez. I work for RSM Australia. I'm currently a security consultant. Previously worked as a computer programmer before shifting my career into InfoSec. So you can check my link in QR code, and my Discord is InfoSec Noob. So what is binary exploitation? So basically, binary exploitation is exploiting the current logic or vulnerabilities that exist within the binary itself. So this could be like missing input validation flows, logic control flows, and yeah, just taking advantage of the current flaws of the binary. Address bus and data bus. So that the CPU has two types of address or channel bus. Typically, they come in pairs. We have the address itself and the data that matches the address. Next one. So the CPU has like in-memory built-in in-memory registers, and for 32-bit we have like can store up to 4 bytes, while the 64-bit can store up to 8 bytes. So let me show you a demo of that one. Let's see what's this. So this one's for the 32-bit. Let's play it. This one's for the 32-bit. So this one for the 32-bit, as you can see on this side, these are the CPU registers, or we call it just built-in CPU memory, which is faster than the like normal memory that we have in our computers, or like the SSD or something. So as you can see, the maximum or the bytes, the capacity that it could hold compared to a 64-bit, which is like almost doubled. And this one. So we have the CPU registers. Next, we have the standard calling convention. So for most 32-bit the client applications, we have the C declaration standard call or the standard call declaration. While on the 64-bit, most of these 64-bit use the fast call calling convention. And here we can see a function, just a simple function, my function, and how it's being called in the main function. So let's show a demo of this one and let's see how are they being called. Okay, let's go back here. So I will just create a simple GUI application. Where is it? This is it. Okay, desktop. Yep, sweet, simple one. Windows desktop. Okay, so this is the default one. Now let's plug in our sample function. Copy and paste. So where's the main function? That's the main function. Let's paste it here. Okay, there you go. Let's copy. And let's call it when we're gonna exit the application. So we can put it here and just save it. So first we're gonna compile it on a 32-bit. Rebuild. Okay, it's saved there, and then let's compile it on a 64-bit. Let's copy that. Should be there. Yep. Let's go to the 32-bit first. And where's our 32-bit debugger? Okay. So that's our 32-bit. So let's go to the memory map and find where's the entry point of our application. So this is the one. And for the most of the instructions will be on this section, the text one, and that's where we're gonna go. Okay, So this is the entry point for our application, and let's just look for the function that we made. So this one, and let's put a breakpoint on that. So it's gonna break there before continues and pass it around, and let's just click play. Play. So this is just the standard application. So it's gonna break when we click this. Okay, so we hit the breakpoint. So as we said on the slide, where's that slide? Oh, there you go. So when calling a function, the parameters are like stored on the stack straight away. And let's see this. So you can see here, this is the stack. So those are the values for the parameter call. And now let's go to the 64-bit. 64-bit. Oh. Okay, let's go to the memory map tab, find the entry point for this one. So there it is, just follow, assemble, and let's look for the function that we just made, this one. And let's just put a breakpoint on that one. Okay, so on the slide, we have for 64-bit, the parameters are stored within the registers and some on the stack. So first we store it in the RCX, then RDX, then R8 and R9, then the rest are in the stack. So let's see if it's true on this. So for this one, let's play it first. And it should hit the breakpoint there. Okay, we hit the breakpoint on the function that we made, and let's check. Parameters are being passed here, here, R8 and R9, and as you can see, we have these 5 and 6 on the stack. So that's it for me. So that's for the standard calling convention for a 64-bit and a 32-bit. Next one. So the canonical address for 32-bit and 64-bit are different. So for 64-bit, we don't consume all the addresses that are available for you, but we only we leave we only have, what's this, like 2 bytes of the given capacity for the canonical address. So we can show this one in the demo here. So we will try to overflow the IP for a 32-bit and for a 64-bit, and let's see if it's true that these ones are not being followed. Let's see for this one. We have the 32-bit. Okay, for this one, we'll just chuck in some random string. We'll be using lots of A's on this one. We'll be using like 1000 A's, and let's see what happens. Let's just type in some here. And let's see if it hit the breakpoint here. So as you can see here in the debugger, we just like chuck in some random letters, and you can see the instruction pointer was been overflown by like lots of A's, like the whole instruction pointer was overflown. And let's see on the 64-bit. Is that checking? Okay. Uh, so as you can see, there are registers that had been overwritten by letter A's, but it didn't overwritten the instruction pointer because it doesn't follow the canonical address for a 64-bit application. And so what is a shellcode? A shellcode is just a piece of assembly instructions that could be plugged in into a vulnerable binary application. So these are the different shellcode forms or example. So we have on the left side the assembly code. So these are the opcodes. And on this side, we have the actual assembly code. And if we want to convert this assembly code into like a string, or we could, we usually escape the opcode using the \x to indicate that it is a hex. And some shellcode are in just plain opcode form. So most of the when doing a binary exploitation, we would be using this kind of shellcode form. And we have the final one, the demo. So we have the 64-bit binary application there, and we have the 32-bit binary application. So we'll open the application, make sure it's working. Just type normal 7. And let's type in the correct username and the wrong password. Failed. Now let's type in the correct password. Should work. So simple login form. And let's copy that and let's open it in our debugger. Let's just paste the directory and make sure it's that. Yep, we just play it. Make sure it's running. And let's just type some random stuff there. Now we're gonna copy just a long string, which is 100 characters of letter A's. Again, we're just gonna paste it, the username. And we hit a breakpoint because it overwritten some of the registers and the next instruction pointer, which is not a canonical address. So this would be the next instruction and it couldn't load it to the RIP. So it just stops there. And some registers had been overwritten as well. So we have, so that's where the last instruction. So we're gonna put a breakpoint on that one. And we'll restart and we wanna make sure that we hit the breakpoint. And we're just gonna paste the letter A's again. And this one we're gonna be using the ERC plugin, which is available for x64 debugger, and it's free. So it's just gonna generate mix of alphanumerical characters instead of letter A's. So at this point, we wanna find the exact overflow of the username. So we're just gonna copy that. And I just pasted there, just a whole straight string. And we're gonna paste it in the username and should hit the breakpoint again. Yep, we hit the breakpoint. And we're gonna check which part of the string so this is the part where the last string was overflown. So that one we need to convert it to ASCII form, and we're gonna search it in the memory. So I just use any online like conversion tool and just use rapid tables and convert it to ASCII. And we're gonna copy that and we're gonna search that in the debugger. So again, we'll be using the ERC plugin to search for the string that was overflown. So at this point, it says the string overflows at 872. So you're gonna, just take that now. And now we know it's on 872 and we're just gonna verify and add some different characters. So we're gonna add B on that one and we should check it in the debugger and should reflect on the debugger as well. So we're gonna paste that one. And yep, we hit the breakpoint. And as you can see, the equivalent of B is 4242. So yeah, so now we know it's working. We know that we could overwrite the EIP next. Let's just restart it again and let's see what happens. Now we're gonna put letters C's in front of the string. And we're gonna check if it's likewise reflecting on the debugger. At this point, we wanna see where the locations of the registers are being overflown. So we could see which one we could use later. So we hit the breakpoint. Yeah, we have the letter B's on the end of the string. And as you can see, the four C's are reflected on the RAX and some registers as well. So at this point, we know that this one would be the next instructions passed to the RIP. And we know that RAX has the letter C overwritten in it, R10 and R11. So this one we could like maybe just use RAX to jump into our next instruction, like we call it gadgets that we could use. So we'll kind of see on the next slide. So for this one, we're gonna insert our shellcode on the 64-bit binary. We'll add a new section. Just 1000 space of a new section. And let's call it my sec. And of course, we need to make this section executable because that's where we're gonna put our shellcode. And let's just create a new one so we won't overwrite the old one. Okay, now we have the new section on the, just want to make sure it's working. Now that we have the new section, we're gonna put in our shellcode in it. So we're gonna look for our new section in the memory map. So that's the name of our new application, the text. And as you can see on the end, we have the new section. Just gonna follow it in the dump. And we're gonna copy our NOP sled. So basically this shellcode is does nothing, just an empty instruction. So why are we putting this NOP sled? Because we want to make sure that every time we overflow or exploit the application, if we land in any address of this binary, we will just like slide through to our next shellcode. So for the shellcode, I download it from exploitdb. It's yeah, 205 byte shellcode. And yeah, I'll just copy that shellcode and it's just a pop-up calculator. So we just copy that shellcode and we just paste it after our NLP sled. Size. And yep, that's our shellcode over there. And we'll save it as a new executable. So we want to make sure everything's checked here. Or you just could click select all and patch. And now let's add with shellcode. Okay, now we have our new section and we know that we have the shellcode in it. We want to make sure that new section with the shellcode is running properly. Let's open the debugger and open that new application. So at this point, we want to check the shellcode is running. So I just like overwrite the first instruction pointer to the shellcode address or the new section. So yeah, we're gonna modify the RIP, just pointing to the new section. Okay, now we know our shellcode in the new section is working. This one. Okay, now we'll just overflow it again, and we wanna find which part of the registers that we could use. So we're gonna hit a breakpoint again where the error stopped. And we're just, at this point, we're just repeating what we did at the first one, but this one, it's just with the new section and shellcode. So we hit the breakpoint there. And we're gonna step into it. So you can see the RIP was overwritten by letter B, and RAX was overwritten as well. So we're gonna use the jump RAX opcode or gadget. So at this point, we want to search the memory address of RAX because we're gonna use that on the input string. We're gonna search the memory where jump RAX is. And we have a long list of available memory address that we could use for the jump RAX. The results are saved into a text file as well in the plugin section. So we're just gonna open this file and just search it from there. So we know that, yeah, that FFE0 is the jump AX, and we wanna make sure those safety security settings are all false. And I usually get the last available jump RAX memory address from that one. And yeah, just copy it over there. And so at this point, we plan to jump to RAX and execute the shellcode from there. So yeah, so we know the jump RAX memory address is working. We want to put a breakpoint there. And we're just gonna restart it and make sure it's working. Yeah, so with the memory address, we need to convert it into ASCII again, but in reverse because Intel CPUs store memory address in reverse order, or what they call little endian. So now we converted the memory address to that one. So that one is our jump RAX. And we're just gonna replace that instead of letter B's. So what's gonna happen next here, once we input this string, it's gonna load up that RAX address on the instruction pointer or the RIP over here. Okay, now we hit the breakpoint. And it's just gonna step. And yep, we hit the RAX instruction. It's gonna jump there and it should execute that string, but it's not gonna load it because it's not a canonical address. So I'm gonna fix that later. Okay, now next one is we're gonna put some assembly code in front of the payload. So for that one, it's just a simple assembly instruction that's gonna jump to our section address that we have created a while, which is the pop-up calculator. So we copy that assembly instruction. Again, we're gonna convert it into opcode first, then convert it into ASCII, and gonna paste it on the string. So that's the hex code for the assembly instruction. And we're gonna convert into string. We need to convert that instruction to string because the payload that we use is string as well. Yeah, copy that. Yeah, I think there's something issue with the copy and pasting here, but yeah. So we have the string form of the small assembly code that we made. So that assembly code is we're gonna put it in front of the payload. So what we have here now is a complete payload that jumps to RAX. RIP executes RAX and it executes the simple payload in front of the string that jumps to our new section. Okay, let's test it if it works. So I'm just gonna paste it there. Just gonna paste that whole string there. Okay. Now we hit a breakpoint. So this one would be jump RAX. And we're gonna do a step into, and that was our code that jumps into our new section. And yeah, you just step up into it and make sure it's there. And yeah, we have the pop-up calculator working. So at this point, we wanna make sure it works without the debugger, just the application itself. And there you go. Calculator executed on a overflow on the username. So yeah, so we used a jump RAX, and then from jump RAX we we created a simple small assembly code that jumps into our new section, and our new section has the shellcode in it. So yeah, so you might be asking, oh, you could just like have put the shellcode straight away on the string and the RAX on the end, but just this one another solution that I just presented. So yeah, thanks everyone. Less than 15. And yeah, hope you enjoyed it.